use the time to introduce myself. So I'm Bollig. I'm from Cornelis Networks. I'm a solution architect here based in Germany for the EMEA region. My background is not in computer science, but in computational science. So I was actually, before Cornelis, I was in computation as a physicist doing large radiation hydrodynamics model on 10,000s of cores for hundreds of millions of core hours on all the tier 1 data centers. I have not personally run on Barcelona yet, but some members of my group have consumed a large amount of the Mare Nostrum budget in 2015, I believe, 100 million core hours, which I think was 1/3 of the machine at the time for a year. So I might be here and now is in a kind of a sales marketing role, but I do have some technical background. Okay, it's getting getting close. So, while still working, so I'm from Cornelis Networks. You probably have not heard of the name itself. It's relatively new. But the technology that it is working on is quite established already. It has a long history. So I will talk a bit about where we're going with the technology going forwards. So we switched to a completely open source approach for software, for management, for hardware. We try to be as open standards and open source as possible. So this doesn't work. Maybe you try. Or should I use the laptop? Okay, need to select the window. Okay, so some disclaimers first. Anything that I tell you is up to our best current knowledge. It may change in the future. So Cornelis Networks. So basically, there are no independent vendors for high-performance fabrics left. There's basically only Cornelis Networks left. InfiniBand is now a part of NVIDIA, and you know that might decide to do some bundling and restrictions. And the technology Omni-Path fabric, you might think it's like InfiniBand, but it's actually not InfiniBand. It's its own separate thing. And we strive to be scalable, high-performance, energy efficient, and cost-effective. So our history, Cornelis Networks is new, but the core of it is actually quite old. So our history goes back 20 years. We started back in 2000 using startups for InfiniBand, actually. But in 2011, Intel decided to buy both the Cray Areas fabric, which uses some novel technologies, and the InfiniBand business from QLogic. And together they formed the best of both worlds. They took InfiniBand and they took Cray Areas and created Intel Omni-Path. It has some technological differences between the two technologies. Now, as you know, Intel is now currently closing a lot of projects. In 2019, they decided to start a bit earlier in some parts and decided to close down Omni-Path. But Omni-Path itself, the technology was still working very well, so it was spun out from Intel. And Cornelis Networks, the old development engineers from Intel Omni-Path spun out and created Cornelis Networks, and they acquired the IP for Omni-Path. And now we are continuing on the Omni-Path legacy, technology stack, and software stack into the future and making it as open and interoperable as possible. So what do we focus on? Our focus is the lowest latency fabric with the highest message rate and a high data bandwidth. So that means that when you add more nodes to your cluster and you scale out, you do not just gain capacity, you still maintain adding performance. So that's why you need the fabric and can't just use any commodity Ethernet, but I'm sure you know this. So how do we try to achieve this? We use best-in-class open fabric or libfabric-focused AI HPC adapters using the latest standards going forwards. We are focusing on radix-optimized high-bandwidth switch building blocks. So we have edge switches, we have director switches, we have a full ecosystem that is ready to use. And our goal is to have low latency at any utilization and scale, which is where the technology from Cray Areas, which became Omni-Path, is really the key differentiator here. And going forwards, if you want to use more advanced topologies beyond trees, you want a dragonfly, you want a megafly, you might want to have a pruned tree, and that's where the advanced adaptive routing features come in the future so that you can drive your bandwidth even when you have some congestion on the fabric. So how do we do it? It's quite simple. We have the entire stack. We have the software, our own software. We have the fabric managers. We have the Omni-Path Express software, which we introduced quite recently. We have our own adapters. We have our own add switches with 48 ports. We also have director switches, which have up to 1,000 ports, which are basically a 2-tier tree in a box. So you can also create like islands of directors connected by add switches or other directors if you want to scale up with some prune tree. We have cables, optical and copper. We try to stay copper inside the rack wherever possible. And we have gateways if you have storage running on InfiniBand or Ethernet, or you have some other fabrics components that are running InfiniBand. We can provide you gateways that connect your Omni-Path fabric to the InfiniBand fabric. The two together will not connect to the same switch. So what is different for Omni-Path? The main differentiator is really in the technology that came from Cray Areas, which is the so-called flow control digits, or short FLITs. So with InfiniBand, you have these big MTU packages. They can be of any size, from 256 byte up to 4 kilobyte or even bigger. But that means that you have very coarse-grained switching that you can do. You need to wait until each MTU package has been delivered. With FLITs, instead of doing these large variable size messages, we have a fixed quantized atomic size, the FLIT. The FLIT is only 65-bit, 64-bit payload, 1 bit is a control bit, and we adapt these FLITs, we pack them together inside the link transfer package. And we can reorder these FLITs, and we can merge different message FLITs together into each link transfer packet. This means that when we have different priority traffic, let's say you have a big storage going streaming through your system, and now you have one collective. And that collective is very sporadic. And you want that collective algorithm to be the all reduce or the barrier or whatever you want it to finish as quickly as possible at any switch hop which it needs to traverse the system. With InfiniBand, you would have to wait until the entire message has finished sending. But with Omni-Path, with these FLITs, you can just interleave these high priority FLITs inside the low priority storage traffic. That means that you don't have any variable latency. The latency is basically has an upper limit. At each switch hop, you can only wait one link transfer packet transmission, or maybe even just a few FLITs before it gets transmitted right to the next hop. This means that we can have much better traffic flow optimization. We can have more advanced routing. These FLITs can take many different paths to the target. We can have dynamic lane scaling. If you have a cable, 2 of the lanes break, you still have 2 working lanes. We scale down the bandwidth, but the link stays up until you can repair it. And we do have RDMA hardware capabilities. There's some discussion going on about onload, offload. We do fully support offloading to the adapter. It's not like some say we only do it on the CPU, but it's not true. So we do have full RDMA support from memory also to GPUs. And we also offer accelerated TCP support. So we have full support for the verbs interfaces in software in the adapter. And we can run accelerated IP, and we can connect your storage using this TCP/IP support if you, for example, have a LNet router or a Lustre file system. So what differentiates us? We are the independent vendor for high-performance fabric. This means that we have no bundling conditions. We can work with you for any CPU, any GPU, if you want ARM, if you want Intel, if you want an AMD system or any combination of GPUs, Intel, AMD, NVIDIA, some accelerators. We work with all integrators. We work with most file systems. And of course, we have a large selection of interconnects that we want to bring out next year. So we can really enable you to use what best fits your use case, not necessarily what the integrator thinks is your best solution. So what we got from Intel was the old software stack. It was technically open source, but it wasn't really fully open source, a full community involvement. With OPX, which is Omni-Path Express, the successor to the old Intel Omni-Path software stack, we switched to a fully open architecture. We fully embrace Open Fabric's interfaces, also known as libfabric, which gives us access to industry standard frameworks without needing to program to any proprietary API like PSM2, which you might have heard of before. And because it's open source development, we continuously upstream every new release of Omni-Path Express to the community, which checks it, verifies it, and puts it into the open community releases done by the Open Fabrics Alliance. And the good thing is, this is not limited to any future hardware. You can test it today already. If you have any Omni-Path installation on your cluster, you can download the software stack from the internet, compile it, and run it. It will work. It doesn't have any dependencies. Just download libfabric. And you can test it today on your existing systems to prepare you for the next generation of Omni-Path, which will only work with this OPX software. So this is how it looks right now. Omni-Path, as I said, currently uses PSM2, which is the old Intel standard. But with Omni-Path Express, we now also provide the OPX provider, which does not only support MPI, but also many other middlewares like partition global array spaces, SHMEM middleware, also DEOS, and also more better GPU support. And this works on the current 100 gig adapters and will also work on the future 400 gig and 800 gig adapters. So what we get from this OFI libfabric ecosystem, because it's an open standard, everyone can program for it easily. If anybody programs their middleware to work with OFI libfabric interfaces, it will automatically also work with Omni-Path Fabric. And that's a real advantage to it. Nobody needs to program anything for PSM2 or PSM3 or any of the other proprietary middlewares. Instead, with PSM2, we were mainly focused on MPI, classical HPC. But as we know, everything is now moving towards converged infrastructures. And if you have a converged infrastructure, you have much bigger demand on what middleware you want to run on it. It might not just be the standard SUSE Linux Enterprise or Red Hat or any of the standard distributions. It might also be like Ubuntu, Jupyter Notebooks, PyTorch, AI frameworks, which do not build directly upon MPI. And that's where OFI libfabric enables us to leverage the community. They develop these interfaces for OFI libfabric, and we can directly benefit from this development. So there's no double work that needs to be done. And because it's open source, if it doesn't fit your use case, you can modify the driver, you can modify the OPX provider, you can really tailor it towards your use case. Yeah. And we also have GPU support. So we'll move away from proprietary interfaces we had before PSM2 CUDA. We'll now move towards interfaces that also leverage libfabric to interface with the NVIDIA GPU Direct, but also for AMD and Intel will use the open standard DMA buff mechanism, which is already included in every Linux kernel installation. So therefore, we reduce the vendor dependence on our software stack. So what does that mean for us? We have, of course, not only just made a new OPX provider, filled it with stuff. No, we've tried to make it as lean as possible. So if you reduce the code instructions that needs to run, reduce the cache contention when you're running the provider, what you get is much better latency, at small messages especially. And that is oftentimes what is important if you run collectives. Collectives are typically not too big. They are a few hundred kilobytes and so on. And at these sizes, you're mostly spending time doing the initialization of the transport, setting up the adapters, getting the memory aligned on both hosts, and that's all latency before you can even start sending. So at small messages, it's not really important how much bandwidth you have. It's just how quickly can you do all the processing. And that also enables us to get much more message rate. So also with collective algorithms, if you have an all-to-all, you get the quadratic growth for communication that needs to go on, and that's where you really need the message rate. And because we use the onload mechanism, so for very small messages, we do not let the adapter get the data from memory over the PCIe bus back down to the adapter over the fabric. Instead, for very small messages, we just let the CPU do it. It's probably already in cache. You just send it directly over the bus. You don't need to have the overhead of telling the adapter to do it, which means that we also have linear scalability of the message rates. So the more CPUs that you have communicating, the more messages you can drive per second. So it doesn't matter if you have 128 ppn or 64 ppn, the fabric always adapts to the size. And if you have a newer generation of CPU, it also becomes more performant at the same time. For example, these runs are done using Intel Ice Lakes. We've also done similar performance comparisons on Intel Ice Lakes, and these message rates, or this is done on EPIC, We haven't done Genua yet, but in Intel Ice Lakes, for comparison, we're down to 0.8 microseconds for one full MPI send receive over one switch hop. So these are quite very good numbers. How does this result in application performance? Here we have compared against HDR. Kim already was talking about his weather applications. So here we have the weather vertical. You can see that basically, even if you have HDR 200, it doesn't really matter that much. Because I said for small messages, bandwidth doesn't particularly matter. For AI applications, it might matter more. But for traditional HPC, latency and message rate is really what counts for the most part. And you can see that even though OPA is only, Omni-Path Express, only 100 gigabit per second, we can actually beat HDR in nearly all workloads. So to summarize, Omni-Path Express builds upon Open Fabrics Alliance, which is an open, standard, and portable API. We are rich in features. We get better support for GPUs, better support for storage. The community can involve themselves. And it makes it much easier because they only need to develop a single application interface that they need to program to. That means we get much broader application support, and it's open source. You can do whatever you want with your software. It's practically your software. And it also means it's future-proof. If some of the architectures change, you have an older driver version, or it's not supported yet, you can do it on your own prototype system, write your own provider driver, and get it working this way. And OPX is fully embracing the libfabric interfaces, so it's programmed for OFI. Most other adapters or most other vendors have their own proprietary interface and then write a shim or a wrapper that makes it work with OFI. But no, our interface is directly written from the software to the hardware to directly match, semantic match, adapter to OFI interfaces. And yeah, it's upstream first. So any release we do of the software is going first to GitHub of the libfabric Alliance. There it's checked, verified, tested for compatibility issues, and only then do we give it to customers. So the community is always verifying any release we do, so we are upstream first, and you can download the current driver version at any time. You just get the GitHub. It doesn't have any dependencies. It will just compile directly as long as you tell it, OK, compile with OPX. It will work. So what we have for GPU support, so at the moment, we have with PSM2 full support for NVIDIA GPUs with GPU Direct RDMA. And we also have support for AI frameworks using PSM2 Nickel. We're currently in development for 2023 very soon. First, we should have it probably something done by ISC. We'll have Omni-Path Express support for NVIDIA GPUs for libfabric. And with Intel and AMD, we are working to get DMA buff working. Of course, Intel GPUs are currently not very available yet, so we can't have any numbers. But with AMD, we have some cooperation to also get Nickel, RICL, the AMD version of CCL, and one CCL, the Intel version, running on our hardware. The host fabric interface driver, so the software that you need to run the adapter itself, is quite easy to install. You don't need to install any kind of MOFET. It runs standard in the kernel. You can use the standard OFET. You don't need to modify anything. Every driver update we publish goes to the community and is accepted by kernel.org, so by Linus Torvalds himself. He says, OK, this works with everything. Let's put it in the kernel. That means that every time you get a new release of the kernel or you stand up a new system, you switch Linux kernels, it doesn't matter, it will always work out of the box. You don't need to install anything. You plug the adapter in, it will be detected, and then it will work. But you can, of course, also download official distributions provided by us. They don't have any additional capabilities, but they are tested. We offer official support for them, and you can get the running, always newest version, because the kernel might be old or you might not want to update yet. You can download the newest version directly from our web page. And going forwards, for Ubuntu, we're already testing it. We'll also offer in-distro packages. So you can also use the package manager to just get the newest version. And the good thing is, there are no conflicts because we don't modify OFET. It will break nothing, and it will just work right out of the box. So switch management, Previously, we were using VxWare for switch management, which was, again, a proprietary software, and now we're switching to OpenBMC, which is just a standard Linux kernel running on the switch, which gives us access to standard technologies for platform support, like Redfish, OpenBMC, which directly expose the useful statistics to you. And the good thing is you can use your favorite monitoring and management tools. You can use community-developed applications that interface with it. And we're also actively contributing to the Open Fabrics management frameworks to give you an idea of where we're heading in the future. So from the hardware side, next year, we're going to 400 gig with CN5000 adapters. And as soon as PCI Express 6 is available, with CXL, we'll move to 800 gig. And with 800 gig, we'll also introduce DPU acceleration. So you can also start to offload your communication or your messaging paradigms off to a dedicated adapter with dedicated chips in it. So a CN5000, this is the 400 gig interface, the 5th generation. That's why it's called CN5000. Omni-Path was 4th generation. We strive to get below 1 microsecond latency. We double the message rate again. And we also switch to an advanced ASIC process. So we move from 16 nanometer or so to 7 nanometer, which allows us to use much more advanced algorithms, which means we get also much better telemetry. Because we use OpenBMC, we have much better insight into power consumption, congestion avoidance, advanced topographies, and all of these topologies, and all of these can be done with the new chip. With CN6000, our 800 gig product, we're reusing the same switch chip, which means that it's fully compatible with Omni-Path with CN5000. So you can start with a CN5000 400 gig fabric, and you can update the cluster to 800 gig, and you can just connect them directly without any problem. They will work. You can bifurcate the CN6000 800 gig to 2 CN5000, and therefore you can also reduce the amount of switches that you need to use. So the DPU, we also use open standard for hardware. We don't use ARM CPUs, we use RISC-V CPUs. And for this, we have many cores on the DPUs. So these are RISC-V chips, and we also have fabric accelerator units. These are basically stream processors operating on the 80 gigabyte per second data stream all the time. So these are basically your fixed function, mildly programmable GPU accelerators, basically. Meanwhile, the RISC-V are fully GP, general purpose CPUs. You can program them any way you want, which means you can use them for application acceleration, you can offload your storage. If you have checkpointing or output files, you can let the computation run in the background, let the DPU access the memory on the host and write it out. Or you can run post-processing directly on the DPU, so you don't have to do an extensive post-processing step afterwards where you need to read the data from hard drive, analyze it, and write it back now. Because we have also these RISC-V chips, we can also do message acceleration. If you have asynchronous communication, you know that if you don't have any progress threads, oftentimes they don't actually progress. They just sit until you do an MPI wait, and only then do they do their stuff. So now you can also use the DPU to tell them to, OK, drive me the acceleration, drive me the collectives, get it done as quickly as possible. Same with compute engine. Same with compute engines. So these are general purpose CPUs. If you want, you can run MPI tasks on the DPU itself. For example, there are use cases where you have a task-based program that uses directed acyclic graphs that allow you to mix and match your processing steps on many different hosts so that you can reduce any kind of imbalance on the system, which is also a case for many AMR grids or weather grids. And because they are, as I said, GP CPUs, you can do infrastructure offload. We do not focus on cloud architectures as for now, but you can also offload virtualization services, hypervisors, multi-tenancy, and so on. Let it be handled by the DPU. That's a use case that we fully will support going forwards. And our main mantra is we always want to accelerate. We do not want to just only do the message library. We want to use as many as possible on the DPU and use it and allow the programmer, the developer, to develop their own workflow on the DPU. So it will be freely programmable. We will try maybe OpenMP offload or other programming paradigms to make it as easy as possible to program this hardware. So I'm concluding basically, so there are 6 Ps where we are good at. We have good performance. We have better power efficiency than HDR. We have a much better price. We are innovating continuously using the FLITS interface, the link layer technology that came from Cray, which allows us to much better congestion avoidance. We are partner friendly, there's no bundling conditions, and we have a very short lead time, a few weeks, not a year. So that's an important advantage for most of us. And we also experience it because we have to buy for gateways. You have to buy our own HDR adapters, and that takes forever with InfiniBand. So if you want to talk to us, you can meet us at ISC 2023. We have a booth there. We can also arrange private meetings if you want. So come see us, and we are very happy to go into more detail for any questions that you might have beyond this presentation.
Thank you so much. Any questions?
You have some performance in user case of distributed storage like Lustre or GPFS, something like that.
Yeah, we
how is the behavior?
The what?
The behavior, the performance, and if it's well, it works well with GPFS and something like that.
We have full support for GPFS and Lustre. You can directly connect Omni-Path to the fabric. For some legacy, we can also support BGFS. For some legacy storage vendors that you have, they can also use gateways. So you can use, if you want, you can run the storage on InfiniBand, have a few gateways connecting your Omni-Path cluster to it. But for LNet especially, we have direct capability, and for GPFS as well. So there are many tier 1 supercomputing centers running Omni-Path with GPFS.
Hi. When you have talked about the gateways that you have to route the traffic from an IB fabric to an OPA fabric.
Yes.
So what's the latency or the performance penalty added to that?
I think in terms of line rate, you get about 90% of line rate. So you basically have a server with adapter cards for Omni-Path, adapter cards for InfiniBand or Ethernet, and they have to go through the CPU to talk to each other. So that adds some overhead, so that you need to take into account.
Yeah, that's a key point, because in order to adopt Omni-Path and integrate in the existing fabric, for instance, with an existing storage infrastructure, it's important to route the traffic there. And second question I have is, you're catching up with NDR in 2024 at 400 gigabit. What will be the switch radix?
It will be 48.
48, so it's an improvement over
it's the same switch radix. So basically, the entire faceplate is filled with ports, so we can't go any more than that realistically without using splitter cables.
So you're catching up. Okay, so it's 48 ports per one you switch, rated at 400 gigabit each port,
yes.
Each physical port.
We can also bifurcate these ports down to 200 gigabit.
Okay, thanks.
Okay. No question. So back in the time, there was some solutions around CC NUMA machines built on top of a low latency interconnect like InfiniBand and so on. I was wondering if you have if you heard about any initiative around this with Cornelis Networks.
We're working with SHMEM systems, so we have some research going on with the big national labs in the US, developing and testing their PGAS SHMEM, OpenSHMEM on our network, and it seems to be working quite well, if that's what you mean.
Yeah.
Okay.
Okay, so thank you again.
Thank you very much.